Yes, so as Peter said, today I'm going to be talking a little bit about CSV parsing. I think the nice thing of this talk is that it goes basically kind of like through the history of DuckDB CSV parsing. So I'm going to show you a little bit of code, some examples, and the differences of performance in that. Of course, there's the slide of who am I? I guess not everyone knows me. So I did my PhD here at CWI from 2017 to 2021, and I had done most of my work on indexes for interactive data analysis with Professor Stefan Monago. And then later on, I did a postdoc here where I did a little bit of automatic data reorganization and zero copy data interops. So basically like how can different libraries in Python communicate data efficiently. Since 2021, I'm a software engineer at DuckDB Labs, which is the company, of course, that provides services on DuckDB. And I did all sorts of stuff there. I implemented the art index. I did the initial implementation for zone maps. I worked a lot in data integrations. So Arrow, ADBC, Substrate, whatnot. I did index joins that unfortunately have been recently deprecated because the hash joins just got so much better. Python API, also I did a lot of work there, and more recently, the CSV reader. In case of doubts, I'm the one with the red arrow. The other one is my barking analyst, Oogie Boogie. So let's start off with the history of DuckDB CSV parser. I said to you that, yeah, this is a more recent thing that I've been working on, but that's kind of a lie. Actually, my first commit in DuckDB in 21 of August 2018. So Hannes is here, so he can fact check me if my history is incorrect. No, I mean, this is correct, but what I'm going to say now. Like DuckDB, I think was about 3 weeks old at the time. Of course, it's 3 weeks old with Mark as working there, which means that it was basically almost a full-fledged database system by that point. I think at the time, if I'm being honest, we had like some aggregations, groupings. Most of it was like the skeleton of logical plants, physical plants, transformers, these kind of things. And the reason I decided to implement the CSV reader at that point is because nowadays the TP-CET generator is built in DuckDB. At the time, it was not. So basically, you had this third-party library. It would produce a bunch of CSV files, and you could ingest it, and bada bing, bada boom, you had TP-CET in your database system. And of course, as good database researchers, we really care about TP-CETs. And even though we only had groupings and aggregations, it meant we could run Core 1SX. And we already kind of wanted to know if we're going the right direction at unit tests or whatnot. So that's the reason I went for that. Here's like some, I don't even know, like C++ Pythonish code that I just built very quickly. That gives you an idea of how the CSV look like at that point. I literally spent 30 minutes on this because, of course, CSVs are easy. You just have to do like some tokenization, figure out the limiters. What's complicated about that, right? So basically, open a file. If you're doing that in C++, it could be like I have stream. You parse the lines, you get a new line, and then you do like a split function to get the values, passing on the delimiter. Of course, this split function in reality also has to check a little bit for the quotes, but in general, like you can imagine, it's very simple. This returns to a vector with the values. Then for its value, do some sanitization of like removing quotes and escapes, and you add that to the chunk, right? So easy peasy lemon squeezy. The way this looks like, you have here a CSV file with my favorite bands. And I want to ingest this in DuckDB. This basically will get the first line. Okay, let's split it up into values. And now you realize, okay, one of them has a quote, so we remove that, and then we can add this to their respective rows and chunks. So not too complicated, also not very performatic. So here you can see this is pre-0.1, and finding commits of pre-0.1 that could be compiled and executed without burning my machine was already a bit of a challenge, but I managed to get there. So here you can see this is loading line item, and I think this all the examples I have in this presentation are loading line item scale factor 10, which is about 8 gigabytes as a CSV file. And then basically the disk I/O is about 2 seconds on my Mac, but this would take 213 seconds. So, I mean, good enough, right? Like you load data once, you want to run your benchmarks there. Like we didn't really care that much about it, I think. At that time, I was like, okay, it's able to read simple, well-constructed CSV files. I say simple because if you go to quoted new lines, this of course gets borked. It accepted the main like dialects options, so the limiter quotes and escapes, the user could define these. Of course, you also need schema definitions. So this is basically a copy from function, right? So your table is already created, you already know the names and types and so on. The problems with this, of course, is that, as you can imagine, has a horrible performance. All these lines split, sanitizer, it's not like very good. It heavily relies on IF stream, so you have no control of what really is in memory. And yeah, you have no control how the file is really being accessed. I mean, that's a bit of a lie because with IF stream, you can actually set, I think, the buffers, but at the time, that's how the implementation was. So it really didn't match like our file system and the way that data should be accessed. And again, it's borked for quoted new lines. And then we enter like kind of this era of 2019 that I call the buffered CSV reader go-to. You can see this was a PR by Mifring. That's the hacker's name of Mark. And the idea here, it was basically like, okay, we actually have states of CSV parsing. So you kind of have your normal states when you're doing a value, and then you suddenly find the limiter. So now you go to this add value states, you find a new line identifier, you go to the add row, you find a quote, you go to in quotes, and so forth. So he changed the implementation to be much more efficient because now like this whole splitting, adding lines is happening with our codes, nothing really depending on the standard library. And he also changed for, instead of depending on IF stream, you actually have your own file handle. You copy that to 32 megabyte buffers, and you are in control of what's actually in memory or not. And you can do things much more efficiently. So if we get again the CSV we had before and we go for the same process, the difference here is that this will actually get a buffer from the CSV. Again, in reality, this is like 32 megabytes, but that'll be a lot of bytes for my slides. So my slides are about 40 bytes, maybe, I don't know. But basically, you get the buffer and you start parsing it, right? So you start from on this normal states, you hit a delimiter, it's like, okay, now you go to the add value. And then on the add value, you actually add the value to the data chunk. Then from the delimiter, you find a quote. So now you go to the quoted states. And then you annotate that, okay, I found a quote. I need to remember to remove this when I go add the value. And then you find again the unquoted, like if you had commas here, they would basically be ignored, right? If you had the limiter, sorry, they would basically be ignored because they're within quotes. But then you find again, okay, this is the unquoted. So now I have to remember to remove the quotes and the unquotes and treat escapes if they happens. And then you find again our delimiter, you add the value. And kind of like so on and so forth, right? Like then it goes normal, blah, 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 you add the line, and then you do some special code to finalize the add line there. All right. And after you're done like with the first buffer here, like at this point, you just did the whole first line and you had the third Jean Lajoie, and you add that as well, you just can request the next buffer to your file handler. So you get your buffer number 2, and you basically continue this process. So since it's like single threaded, it's pretty easy. You just go over the buffers in one go. As you can see, there was quite a good performance improvement from my 20 minutes implementation to Mark's more advanced state-based buffered implementation. It was actually about a 4x speed up. And that was really like good enough. Like at that point, the code was also able to read all well-constructed CSV files. So now there was actually code that took care of quoted new lines properly. You have full control, again, of parts of the CSV that are in memory. You have pretty good single-threaded performance. I mean, this was like a 4x speed up. Seems pretty decent. One of the problems is actually horrible to debug because of these go-to functions. You don't really know. You lose a lot of information of how you got into that state. So I suffered a bit of that afterwards. It's very brittle in a way because All right, so you read all well-constructed CSV files, but it turns out that CSV files are not well-constructed. And these manual settings are a pain, right? Like you still need to set up like headers, what are the types, what are the dialect options, and so on. So to give you an example of why CSVs are not well formed, we have here a tweet for a famous database researcher that's also in this room, Hannes, that got his bank statements from Rabobank, and they forgot to escape the quoted values of his bank statements. And then saying like, hey guys, okay, how can this happen? This is pretty much impossible to read. Rabobank Saskia replies, Hannes, have you tried Excel? So this is the thing. Like this is the reality of CSV files is that people are just exporting them from Excel. So you get like all kinds of weird stuff. And I'm gonna show you guys some weird stuff that gave me a little bit of nightmares in PTSD, but I hope you will have fun anyway. So this is a picture of a real-world CSV files enjoyed the freedom of not adhering to RFC 4180 standards imposed by society. You can see they're just like over the fire. Some of them have eyebrows. Some of them have one eyebrow because this might have been AI generated. Who knows? But they're just like enjoying. It's a bit of like a Woodstock kind of thing. You know, you don't really have any rules there. And that's how I call it Woodstock era. And I really like this one comment from Hacker News. This was actually from Jordan's blog post about MotherDuck. And there was like, yeah, you know, like the reason that I think Pandas was very successful is that the performance in a single machine was good enough and they could ingest 99% of CSVs known to humanity. And I think that's not an overstatement. It's like, yeah, I kind of agree with that. And the guy that started this trends and change in DuckDB is Theo. He's unfortunately not here today. So he lost the slide that I praise his work, but he did a lot of like this auto detection, like trying to be able to parse weird stuff in DuckDB. This is not really the scope of the talk, so I did a blog post because I also did some performance changes in this code last year. So if you want to know more, you can check the DuckDB blog post. Yeah, so this Woodstock era again is like really the focus is on auto-magically reading CSV files, right? So instead of like setting all these things up, the idea is you can just have like a from, a path, you read your file to a relational database. So types, names, dialects are automatically inferred. And you have a lot of these options like ignore errors, where you can skip lines if like things are really like broken and you cannot recover from it. So you have no padding. It's like, oh, my column here, my row here is missing a column. So instead of ignoring it, I padded with no, I ingest it in the database and things are good. And you have skip rows. It's like, okay, there's like some dirty rows on top of my file. I can just skip them. And this is also auto-detected. And now I'm going to show you my PTSD a little bit. So these are like all kinds of sorts of files that we see, right? Like there's CSV files where you basically have like a bunch of gunk on the top. Even worse, like some CSV files can actually have comments annotated through the file with like a hashtag or whatever. You have missing columns. So here, as you can see, yeah, the second line is missing the release. So basically like here, if you had the new padding option set, you can see that would actually be added with no. You can have too many columns. So this is a CSV reader, and you have like the little delimiter hiding one of the columns and everything burns. That's very much a reality for a lot of CSV readers, but not DuckDB, hopefully. And you have missing quotes. So basically here, like you start quoted value, but you never finish it. You have non-UTF-8 characters. Oh my God, man, I hate this. I hate this with all my might. And you have like other weirdness stuff, right? So here, for example, we see like, okay, you have a CSV file with 3 columns and some empty lines in the middle. How many lines are in the CSV file? This is a question for you guys. It's not a tricky question, I promise.
There's 3 lines of data.
3 lines of data, perfect. That's the correct answer. But now if we have a single column, how many lines do we have here? A, 3. Who thinks 3? No one thinks 3?
I think 5. Yeah.
1. Okay, 4. Who thinks 4? 4. No one thinks 5. Everyone thinks 5. Yeah, 5 is the winner. Well, the answer is 4. The reason that it's 4 is because if your new string is actually set to an empty line, and that's the assumption here, of course, the second line becomes null because it's a single column. But for whatever reason, the last line you don't count. So if you had like 5 last lines here, only the last one would count, the other ones would become null. Why? I don't know. God decided that. I don't know. When I got here, I had the golden plates. That's all I can say. This one here, what is this wrong
You
even?
mean this is according to the RFC?
That's according to systems readings.
Okay.
So my theory is that Excel probably just adds an extra line there because why not? That's fun. But I'm not exactly sure. This one is also cool. So if you have a CSV file, how many columns does the CSV file has? 3 or 4? 4, 3, 4.
DuckDB says 4, I say 3.
No,
CH says 3.
both are actually valid. So in reality, in DuckDB, if you do like a select star from this, it will be, I think, 4 columns. Man, I implemented this, but who knows? But if you have a creates table that has 3 columns and you read from it, it will also be accepted because all the values after the delimiter are null. Again, why is this valid? I don't know, man. Go figure. And then, of course, I call the Woodstock arrow was kind of the option explosion in DuckDB. So these are the number of options, as you can very easily read from all the way in the back. There are approximately 30 options today to access it. And what I think it's more fun is that 17 minutes ago, I got someone else asking me to add a new option. That was actually not 17 minutes ago. It was like 5 days ago. But I average it out that every 2 weeks, I have someone asking me for a new CSV option. And then I need to be like, really? Okay, show me systems that have it. Okay, no system has it. No. So that's kind of like the default procedure. I have that. And the other thing that I want to show is that like, okay, so basically all this Woodstock era kind of took about 4 years. There's like a lot of like this detailed implementation that went through these years. It's not like someone was working only on that, but we're all like putting a little bit of effort. And the interesting thing is that there was not really any kind of performance driven implementation there. There's only like a 10% speed up. It was really like about let's try to read some weird stuff. And then I have the parallel state machine error. So basically, I was in my office one day, and then Mark came and was like, "Hey, Pedro, like you've been working on like parallelizing scanners for a while. Would you like to give it a go to the CSV scan?" I'm like, "Yeah, sure, whatever." Like it's just like you give like because every scanner is like this. Thread 1, you read from line 0 to 10,000. Thread 2, 10,000 to 20,000 or whatever, right? Like it's pretty easy. And then I was like, "Yeah, sure, man, I'll do it like I don't know, next month." And the release was like a month later or something like this. And then he was basically like this. One does not simply parallelize CSV scans, kind of like you're going to mortar kind of vibe. But I gave it a try anyway. And I'm going to show you like a little bit of the architecture of how this parallelization works, right? So basically you have a CSV file, you create a fire scan. This fire scan basically is connected to a CSV buffer manager. That's the guy that's like getting the buffers and caching them and passing through the other steps. So basically the CSV buffer manager starts getting buffers and passing to the CSV sniffer. The CSV sniffer again is like the guy that determines the dialect and whatnot, right? Like it's like the Woodstock resolver. And then basically go with buffer 0, buffer 1, how many buffers are necessary. And from that, you get a state machine. I'm going to go over the state machine later on, but you can think of it as something that you can set it up with these delimiter options and quotes and escapes, and it allows you to efficiently parse the CSV file. But then with the state machine, you create kind of like this CSV scanner, which is a global guy that tells the little threads what they should be working on. And in our case here, we have 6 threads. And in DuckDB, the way it works is these buffers are 32 megabytes, and each thread will always work on about 8 megabytes. So you can see here, for example, that thread 1, hopefully you guys can see in the back, but thread 1 basically gets like the buffer index 0, and it reads the first 8 megabytes. So it starts from byte 0 to bytes until 8 megabytes. Thread 2 then gets the same buffer 0, but goes from 8 to 16. Thread 3 gets 16 to 24, so on and so forth, until thread 5 gets buffer index 1. And thread 6 gets a buffer index 1, but like 5 reads from the first 8 megabytes. and thread 6 reads the subsequent 8 megabytes. And then when thread 2 is finished, it basically gets the next one in the pool, which would be buffer index 1, but now from 16 to 24 megabytes. That's basically how the parallelism works. Of course, what makes it difficult is that on CSV files, you don't really know where lines start, right? Like bytes 8,000 or 80,000 or 800,000 doesn't really mean anything. You can, by luck, start at the line, you can be at the middle of a value, you can be anywhere, right? So to illustrate this, I have this example here. Again, these buffers are not 32 megabytes, they're much smaller. And this is basically my favorite bands, but I added this one bands so I could add this example of a quote a new line. I think it's called Simon Garfunkel. Yeah. Oh, Peter agrees. Good.
Yeah.
So I'm on the right track here. And then basically this file would have these free buffers, right? So if we start
The song has Sound of Silence.
Sounds of Silence, yeah.
Yes, it's
And I think so. So the way this works, like, okay, we start off, let's say, with 4 threads, buffer 1, and we divide buffer 1, like, okay, thread 0, we go from this point to this point, thread 1 to this point. So this point you can see illustrated in the figure, right? That basically means that, and here is where our new line delimiters are. On thread 2, the new line delimiter is an actual new line delimiter, like that separating a row. On thread 3, you have one that's actually in the middle of a value, right? And the basic idea is that because we ran the sniffer, we actually have information about the schema of the CSV file, right? So we know the CSV file has 4 columns. We know the first column is a big int, the second column is a varchar, the third column is a varchar, the fourth column is dates. So basically the way this works is like thread 0 had started only be able to read until the initial of the from the peak of destiny. But the rule is a thread must always read until the end of the line. So it will go over its boundaries set by the global scanner to finish off that line properly. The other rule is if there's not a new line in the thread actually does nothing. So in practice, this would start at the E from the, and go continues there until trying to find a new line where it could actually start its parsing. So since thread 1 doesn't find anything, it actually doesn't really output anything to data chunk. And then the thread 2 does the same again, right? So it starts like at the delimiter and goes from the delimiter to 006. Bam, I found a new line. So I know that I must read the next line. So thread 2 reads then the 2 until the end of Sounds of Silence, 1966. Thread 3 then is in trouble, right? Because now it's like, oh, damn, I started at the I from Simon, but I'm going to walk to the new line delimiter. I found it, but it's actually in the middle of the value, and there's actually not a new line delimiter. So what it does is like, it will get Garfunkel, it will properly parse this, but when it tries to match our schema, it will figure out like, hey, the first column is actually not a big int as we had thought, and we actually don't have the correct number of columns. So this is not the start of our CSV file. And then basically it will not output anything because it's again outside of its boundaries.
But well, suppose that Simon and Garfunkel would have been the first column, so band would have been the first column and ID not. Then it could have thought that this was a full line. It would just have missed Simon.
Absolutely.
And actually they got into a big fight and they don't talk to each other and they are actually separate.
Split. Oh no.
It's an actual state of affairs.
So there's absolutely ways,
But the way I think that's more robust would be to say, if you parse a line that the previous thread also claimed, but the previous thread claimed a larger part of it, including Simon, then that one should win, basically.
Yeah. So the way it happens in practice, like definitely there are ways that you can you can even have situations where you basically have again your schema matching inside like a new line value or whatever. But like in your example as well, what we actually have in DuckDB is a validation step. this validation doesn't really fix the issues, but throws an error actually. It says like, hey, dude, like I can't parse this right now. And has been there for a year and a half and no one has shouted at me. So I think this just like seems to not happen. If it happens eventually, you can open an issue, internets, you can tag me. And I might ignore it. No, I'm joking. I'll have a look at it. And yeah, like I think I had this idea as well. It was just like kind of out of the scope of time I had at the time. And since no one complained, I kind of ignored this issue. That's how my mind works. But anyway, so the difference is, yeah, of course.
For the slide, so thread 2 in this example does nothing, and thread 1 reads until after 2006, right? Yeah.
19, so yeah, exactly.
Okay.
In reality, this is not really a common case. So the buffers are pretty big, and then you basically need a line that's over 8 megabytes, which again, sure, like it can happen, I guess, but no one has opened an issue threatening my life with that. So for now, yeah, there's basically like kind of this can happen. Then the thread won't. This will actually work. The thread will just not output anything actually, but there is a limitation that I have, not from a technical reason, but more also to simplify things. Is that a line must always fit. You cannot have a line that's bigger than the buffer size. So you cannot have one line that's over 32 megabytes. That has not happened yet. If you have a CSV file, that's the case, please submit it to me so I trust you, because I don't believe that happens.
I can make one for you.
Oh, that's not allowed. It needs to be real data. That's the challenge. So here's like how this looks like. Again, this parallel model has been released for a while already in 0.8, I think more than a year. And again, it kind of like got another 4x speed up from what it had in 0.7. That's again like running on my MacBook. So now let's go for the state machines, which is kind of what I promised you guys.
Can I ask one more question about this?
Yeah, go for it.
So when this happens at the end of the buffer, then the thread would just read into the next buffer.
Yeah, absolutely. So that's a great question. And these are actually one of the worst things that can happen is if you have what I call an over buffer value. So if your value ends in this buffer and continues on this other one. So this is like the biggest minefield of bugs and issues that you can find in the parallel CSV reader. And these were a lot of work to get this very rounded properly. But yeah, like basically if your line is not over in the buffer, you will look on the next buffer. And that's also why it's kind of nice to have this buffer manager for the CSV files, because not only you're using these buffers on this sniffer and you can cache them and use them again when reading, but you can also like have different threads looking at different things at the same time.
It's also the source of the limitation, because the buffer manager needs to link to the line.
Yeah, absolutely. I mean, in the end, this will depend a bit on the number of threads you run. If you have a big cluster, you need like more.
Right, but I mean, like you hold something and you try to finish it, but you don't release until you're done because part of your data is there. But you also want a maximum size for the buffer manager to have something in memory. And that's because of these 32 megabytes, I assume.
Yeah. So all these buffers, they are 32 megabytes, but you can have more than one buffer in memory. So you can have more than 32 megabytes. So for example, if you have, let's say 32 threads, then you're gonna need a bunch of buffers to keep all these threads busy. So yeah, that needs to scale a little bit with your computational power. Anyway, so 4x speed up, cool. Transition triggers. Okay, back to the state machine transition. So as I told you guys, I kind of disliked the way that the states were defined before with all these go-to operations. So I decided to add a simple state machine to do the parsing. And here on the left column, you have the states. So they're very similar to what we've seen before. You have like standard state there again, that's like the thing that's doing the value. The limiter state, so we found the limiter, the code states, and you have on the top, the triggers, right? So here, for example, letters A to Z, if you are in a standard state, that will bring you again to a standard state because it basically means that you're parsing that value. And then if you find a comma, that means and you're in the standard states, you go to a delimiter states because now you have to handle that delimiter. And then now you're in the delimiter states and you find again another letter from A to Z, you go back to the standard states. This is a bit of a simplification of how the state machine actually is in DuckDB. There are more states there. Of course, also these here, I kind of like hard-coded the delimiter, the quotes, and the escape, but these can be, these are discovered by the sniffer. So you can generate like a bunch of different state machines depending on your configuration. And again, this is kind of more or less like how the code looks like now. So basically you have this process function on these CSV scanners that run per threads. They basically iterates over a buffer, right? So this 2 pause here would be like your buffer boundary where you stop. And you have a state machine and you have a transition. This transition basically changes like the states for it. And then you have a big switch case that does specialized code depending on which state it is. You increment the iterator. And from there you continue. The idea originally as well of using the state machines is that I had thoughts that we didn't have that many states when I started implementing this, and I had the idea of implementing a predicated version of the codes to avoid all these branches, yes. But it turned out that yeah, performance-wise, it seemed that it was not better. So to give an example of how the state machine works, again, we have the same file, same buffer. We start off with a not set states, which was not presented here, but exists. And then you basically see the first value, you go to standard, you see the second value, it's a delimiter. So you add that value to the chunk, you continue from the delimiter, you see like a T, which is again from like A to Z, so you're back on standard, and you go like the whole tenacious D, it's actually only on the standard state, right? Then you hit a delimiter again, you add it to the chunk, so on and so forth. So you can imagine like what the process is here. It's basically just like checking what the transition is, what the state is, the current states, and transitions trigger different values. And this is the performance of how it currently works now. Managed to get approximately 3x speed up compared to 0.8. Some of it is because of this change for the state machine. Some of it is auto optimizations that were also done that I'm gonna go over them in a bit. But I think like the idea of changing for this state machine is that it's also much more debuggable. You have much more information where you are. Now, it takes me 20 minutes to fix a bug instead of a day. So my life improves. So I'm happy with it. And over the time, we had 100x speed up from my 20-minute implementation to what it is today, which I think is also pretty nice. So extra optimizations.
You just said that the branchless version didn't really give you a speed up.
Yeah.
Do you have any clue why? Or
it's just a lot of codes that I had to do because basically I started like predicating like as any state could be happening in one piece of code. And again, initially I thought it was not going to be that much, but it started to become more and more and more instructions to the point that, yeah, branching is more efficient than just predicating the full code. Maybe there's still like some kind of situation that can find. One thing that I still think it can be interesting is that the sniffer can detect so much from the file. So maybe you can detect certain situations where, for example, you don't end up with so many states or you don't have quoted values, for example. So you don't have quoted, you don't have escapes because your data just don't have any quotes. And then you can suddenly use something predicated that's more efficient. But that's, I don't know, a problem from a future master students. So some extra optimizations. Oh, this one is like one of my favorites. So after implementing this, I realized that a lot of time was being wasted on this transition skipping that I call like useless. So basically when you're going from the tenacious D, you're basically always transitioning to this standard state, right? Like nothing is really happening. And then I ran instruments and then I could see that my process in my transition, so these are the two top lines there on my instruments, they were taking most of the time. And I was like, I don't accept this. So what I did was, the realization here is that when you're in the standard states or quoted states, so for example, also if you're parsing the peak of destiny, is that not every value really matters. Like there's some values that you know are going to trigger some kind of transition if you don't, even if you don't know what that transition will be. So then in this piece of code, there's basically two things happening. One, I do a check for every 8 bytes to see if in these 8 bytes, there's any of these values, right? Is there the limiter, new line, the carriage return? There's some bit magic going on there. I'm not going to go into details of that, but that's basically like you suddenly are able to skip many more bytes than before. And the same thing, and there's like some more specialized code for a smaller data size there. And of course, like this idea was not mine. This actually came from someone in the room, Professor Bones. I was drinking with him, and it basically like he came like this Jedi kind of like use bitwise operations, Pedro. And I was like, oh, that makes sense. So I got home, still a little bit drunk, and implemented that, and gave a pretty nice improvement, like something like 30% improvement or whatnot. Maybe not 30%, like 25. So pretty good. There's this other one that's called implicit casting, or that's how I like to call it at least. So basically, of course, like if you have a schema with different types, you need to at some point convert the strings from a CSV file to these types, right? Before I started doing like this state machine thing, what we had was like this flush operation. So basically, when you parse in the CSV file, you're adding it to a chunk that has a bunch of varchar columns. And then on the flush, you do vector casting, and you cast these vectors. That's, of course, not very efficient because you're suddenly creating all these strings that you don't really need to do this casting later on. So basically what I did was in the process, I implement casting now directly when I'm reading the string. And then there are still certain situations that you have to do this flush. So for example, the basic types, they are all casts from the buffer string. So if you have integers, dates, timestamps, floats, whatever, right? Like the things are more simple. But if you have nested types, this still goes through the flush because there's not really specialized code for it yet. Or if you have dates or timestamps with masks that are not our default mask, they will also get cast at flushing. And then again, this can bring like, this again for TPC8s and can get to like some pretty good performance boost by doing this cast early on and avoiding all these string allocations that were unnecessary.
Well, what is nested types in CSV?
You can have lists, you can have...
In the CSV, it's strings, right?
There are strings, but okay, so you have a string representing a list, right? And then you can have, you can set up, the sniffer won't detect this, but you can set up that the column type of that column is a list of integers.
And then you try to cast it.
And then this will be cast on the flush.
I see, so that's DuckDB.
And this is, I mean, yeah.
No, cool.
The last optimization I'm going to talk about is projection pushdown. It's really not that crazy. It's very common that people actually do not use CSVs as a loading step, but they actually run queries directly on CSV files because of their workflows, memory limits, disk limits, I don't know. You can find many reasons to do that. So for example, here we have just accounts that wants to get like distinct bands from my greatest bands.csv. That basically means you only really want to check this one column with the band names, right? So what you can do is that basically when you're parsing the file, you can count which column it should be. And it's like, okay, this is the first column. That's not really what I'm interested on. Oh, this is the second column. This is the band name. And that one, you do the whole process of like putting it in the chunk. This looks much easier than it actually is. Because again, you guys need to think that all of this has to work with the weird stuff, right? So you have to work on files that you don't have enough columns, that you have too many columns. These values can be between buffers. So all this really complicates the implementation of that, especially I think for null padding, this was a bit of a nightmare to handle it properly. But this can bring you great performance, right? So basically this is again TPC8's line item, but here I'm just doing whatever, a sum on the first column, like some kind of aggregation on the first column. And basically you hit like this IO. Like that's basically the best that you can get here. So it can bring great performance, especially because CSV files are also very wide. Again, they usually come from Excel, so you get lots of columns. So what the future holds, here we have again a picture of Excel encoded CSVs using UTF-8s. This is where we would be living now. Unfortunately, that's not the case. But I've been working on this thing called regex tables. That's how we call it in DuckDB now. It's kind of like structure error clean. So here in the left, for example, we have our CSV file. It has 3 columns, A, B, C. One column is column A is just an integer, column B is just an integer, column C is just a string, quoted string in this case. And then you can see there's multiple types of errors here, right? Like on the 3rd line, you're missing a column. On the 5th line, you have an extra column 5. On the 6th line, you have a blah where it should be an integer. On the other one, you have unquoted value. And on the other one, you have an invalid UTF-8. And the idea is like when you have ignore errors on, you can just ignore all these lines because they are borts. But of course, they are also wrong, right? So you want to be able to do something with it. So the way this works is that from like a read CSV function, you now have this store rejects variable that you can set up. And then if you read this file that I just showed that I called Pedro's personal nightmare, it will basically store information about what was rejected about it. So you have first this reject scans table that basically stores information about the file that got wrong and the configuration of the scanner where these errors were found. And you have what's more interesting, the rejects errors. And this has information about the errors that were rejected. So you have the line where it happened, you have the byte position of the start of the line, you have the byte position of where the error actually happened, you have the column index, column name, you have error type, you have the original CSV line, so this is not reconstructed. This is the actual CSV line where the problem happens, and you have the error message. And I say you have because I PR'd this yesterday, it's now fighting the CI gods, and the reviewer Mifrin. So as soon as I'm done with my battles, this will hopefully get merged. And the idea is that now people will be able to clean up their files. I mean, you can imagine because you have the byte position of where these errors are happening. You can even write like a simple Python scripts that cleans up your data for you. And the funny thing is that before doing this, I got some of the most common data cleaning tools. And I thought it was very interesting that although they look like for semantic errors or whatnot, this kind of structural errors were just ignored. And then you basically load your borg CSV file and you can't really do much because it's completely broken. So I think this is something that's pretty cool and hopefully useful to people. The other big thing here is async IO. So our CPU users, as you can see here, they're kind of far from being 100%. The problem here is that, of course, like we're interleaving IO in data processing. This is not a problem that is exclusive to CSV files, but to actually any files that you will access through DuckDB. It's something to be fixed at the file system level, but this is something that we will hopefully be looking into the near future. CSV parsing and testing. So that's what was the question? Sorry. That's the thing. Like I believe that doesn't matter how fast you are, right? Like if you can process a file, you can process a file. So I think this is like kind of the next big thing of CSVs in DuckDB is that we need to build a fuzzer because you can think of, you kind of know the things that can go wrong, right? Like I showed you the types of errors, for example, and you can build a fuzzer that can create all sorts of kinds of borg CSV files. And because you're creating, because you're inserting these errors, you know exactly where they're happening. So you can test not only if the CSV reader is correct, but you can also test if the rejects errors is correct. Because the way it works now is that I either get gigantic CSV files from the internet on an issue, and I'm talking about gigabytes, and then I have to manually kind of like figure out where things are going wrong, and that's not very much fun. Or I have to write them myself, and I'm a terrible CSV writer. Like, oh my God, it's not good. And especially, this is a bit more related to DuckDB, is focusing on these errors that happen in between buffers when your values don't fall in one buffer. That's really where the thing has to go. Faster dialect detection.
Yeah. You think about playing around with the buffer configuration rather than playing around with the data?
Yeah, absolutely. So you can actually set the buffer size in DuckDB. There's an option for that. Hopefully undocumented, because people don't use this option, okay?
How about varying buffer size? They're not all the same.
Sorry?
So some buffers are small, some buffers are big, right? Because your correctness algorithm should deal with all of that.
Yeah, no, that I don't do. But you
think that will be evil and probably exposed to us. Because I think
your logic is sound, no matter what buffer size are.
Absolutely. That should work indifferent of the buffer size. Currently, only with the limitation that a line should fit in a buffer.
Yes.
So what I did and what I have for testing is that I have codes that basically identifies the line size of a CSV file, like the max one, and uses that as a parameter in the CSV buffer, and then it goes from that up to 10 other levels and tries to run the CSV file and checks all the results.
Right.
But it's still like this basically goes only on the CSV files we have at DuckDB. It's somewhat limited again. Like I fully agree with you. Like this is kind of like the weird stuff that needs to be executed here.
That's what I meant by your buffer size still uniform per round.
Absolutely.
One buffer is small, one buffer is big.
I fully agree with you.
Yeah.
With the again only with this limitation of the line size, but absolutely. And maybe you wouldn't uncover lots of weird things that are going on. Absolutely, I fully agree. And I really think like this should be like kind of the next focus, the next big focus of CSV reading DuckDB. Faster dialect detection. So I talked a lot about the sniffer. There's still like a lot of low-hanging fruits there for optimization, especially because dialect detection can actually be one of the major bottlenecks of CSV reading. So we currently only really sniff, I think, 10 data chunks. So that's 20,000 rows of the file, but sometimes you have weird stuff happening like in this one line of the CSV file. Then you want to set it up, the sniffer to run the whole thing. The sniffer is single threaded, so it can get pretty slow. Also, I made sure I optimized a bunch of things, so I decided to activate the sniffer for multiple files if you have a scan of many files. But if you have many files, and there are people that have like thousands of files in one scan, I joke you not, this can also become then a bottleneck. So there's a couple ideas already there, like doing parallel sniffing, there's nothing really stopping you to do it parallel. Or what I call like lazy sniffing. It's basically like, okay, if you have a bunch of files in the same scanner, just accept the dialects from the first one, try to scan it, did it, got bored, everything burned down, then you run the sniffer. So these are kind of like the simple ideas there. And there's, of course, like lots of things that can be done in caching, partitioning. There's a lot of work from Anastasia Alamaki's group. I think they even have an academic system as a RawDB or NoDB. That basically the whole idea is that your storage is actually these files, these CSV files. And when you access them, you start like creating certain indexes or create some metadata that allows you to further access them again. So this is something that we could also do. I think it's not uncommon that people keep running queries on the same file. Exactly what kind of information we would like to store remains to be seen, but I think this is something that, you know, for certain cases can bring like another 10x or whatever performance. Yeah, I go to my conclusion now. Man, I hate Excel, that's all I can say. But I love CSV files, apparently. So conclusion, CSV files are here to stay. They will never adhere to any standards. They will always be borked. That's how they work. Like my grandma can open a CSV file on her laptop and add a delimiter. People will do that. I believe that performance-wise, that's not really another 10 or 100x we can get from base scanning. And what I mean by that is that if you're like reading one big CSV file on your machine or a couple files or whatnot, I mean, you can of course like find kind of corner cases where you can get this type of performance benefits, but I think in practice, that's more or less where it is. So that's why I'm also not that worried about performance anymore, but I'm more worried about robustness and about reading weird stuff. It's more important to be capable of read weird files than to be the fastest system. The other thing is even well-constructed CSV files can be hard to read. So as I showed you in my first implementation, I didn't really care about coding new lines. I'm not going to name any systems, but there are systems out there that people use that also still can't really handle that very well. So it's not only broken files, but even well-constructed can be difficult. As data practitioners, avoid CSV files. They are only for the normies and for my grandma. And my bold 20-year prediction, because of course, like I'm at CWI, Research Institute, so I need my bold prediction, is that in 20 years, probably cut this to 5, but I think I'm being, anyway. No one will use Parquet files, but CSV files will still be there. And what do I mean by that? CSV files are here for a reason. They're easy. And you can't get much easier than CSV files. You open them in the freaking test editor or Excel, Hannes. Remember it when you open your bank statements. The Dutch are weird. They have quoted values in their bar names, no? So they will be there, but Parquet file is a performance-driven file. No one has a Parquet file because it's simple or because they can just like open it and start like changing it. And performance also changes, hardware changes, compression algorithm changes. I know there's Peter, for example, is developing a new storage format. Maybe in 10 years, the storage format will be the DuckDB file format, which is a performance-driven file format. I don't know. But what I can tell you is there won't be Parquet. Maybe it will be Parquet 2.0, 3.0, whatever.
2.0 exists and is dead already.
Oh, see?
Already dead for 10 years.
The future is now, old man. Yeah. That's kind of it. I hope it was fun. I hope it was enjoyable. I hope you guys had a laugh or two. If you want to talk to me, you can find me on Twitter. I'm the guy with like the dog looking at the DuckDB flag from the outside. You can also just drop me an email, internet, if you want to ask a question you're not able to ask today. Just text. That's going to be perfect. Thank you so much for listening, and I hope you guys enjoyed.